current carrying, and if we end quickly, we'll end quickly today because I'm also not doing that good. After 1 week, today I'm feeling a pain. Current carrying circular loop as a magnetic dipole. Children, this is very easy. What we are trying to say out here is that there will be a current carrying circular loop, and this current carrying circular loop will be viewed by us as a magnetic dipole. Means you're going to see it like a magnetic dipole means the two poles of a magnet. You'll see a north pole, south pole. Typically, you'll see it as a bar magnet. And this is not something new that we are doing out here. If you go to grade 10, then you remember the CWS, clockwise south. So every loop has got a south pole and a north pole. So the same concept that we will do out here. So you can write down current carrying circular loop as a magnetic dipole. Just write down the idea. I'm not writing that statement that you write. The idea is circular current carrying loop. The idea is a circular current carrying loop. A circular current carrying loop behaves as a tiny bar magnet. A current carrying circular loop behaves as a tiny bar magnet when viewed from far away. Okay, when viewed from far away. When viewed from far away, and you will understand why this far away clause was put. Far away. Children, the takeout that we will do from this understanding is, if you see an electric dipole is constituted when two equal and opposite charges are separated by a finite length and equal and opposite polarity. So that's why in electricity we have a unipole concept, means a unicharge. But a magnetic dipole can exist only when north and south pole are together. That's why in magnetism, the unipole concept is not there. You can't get a single north pole, but you can get a single plus charge or a single minus charge. Okay. Now, so how do we, this is an understanding, not a derivation. So the first thing we say is magnetic field. Magnetic field due to a current carrying circular loop. Now this is a derivation that you have done. Circular loop, this is given by B is equal to mu naught I r square divided by x square plus r square to the power 3 by 2. If I'm not wrong. Yeah. Oh, there was a 2 also, sorry. 2. This is magnetic field due to, now you remember what is this? This was this. There is a current carrying circular loop, and then there is an axis, and there is a point P. The radius of this loop is r, right? And x is the distance along the axis of the point P where you are trying to measure the magnetic field. This was the expression, right? Now, what did we write immediately at the start of the discussion? We said, when viewed from far away. So when viewed from far away, we will put that clause now. What does that clause tell me? At a far off point. Far off point. So at a far off point, what will be the mathematical implication of that? We will say x square as a value will be sufficiently large than r square as a value. At a far off point, x square as a value will be sufficiently large than r square. Look at the figure. X square will be very big. So in this case, I will say my B now reduces to mu naught I r square divided by, we have this r square is negligible now, so it will be 2x square, so it will become 2x cube, right? It will become 2x cube, making this portion smaller now, else we won't be able to. Okay. This is just understanding. It's not a derivation. It will take that part also. Hey. Yo. So 1, 2 is done. So let's see at 3. Now at 3, what we are doing at 3 is that, see, when the radius is very small of any coil or anything, and you're viewing it from far, far away, radius is appearing here as r square, means it's coming as a 2D element. R square and a square are almost same, because what is the definition of area, you tell me? Pi r square. R square itself is small, so pi r square and r square are almost similar. Have you understood? Because you are viewing from very far away, right? And you have taken this condition where x square is much greater than r square. So our third condition will be that we will say replace r square by a, not a square, huh, children? We are replacing r square by a. So a is equal to pi r square. Therefore, r square will be equal to a by pi. Why has the a been brought? Why did I do this a? Because the IA will give birth to M. End of the day, you want to have the magnetic moment, right? So your definition now becomes B is equal to mu naught I A, and r square is equal to a by pi. So there is a pi out here and an x cube out here. Mu naught I A by x cube. 2 pi x cube. Oh, we should have the 2 also. Yeah, 2 pi x cube. Okay. Now out here we will, step number 4, we introduce magnetic moment. Introduce magnetic moment. And what is magnetic moment? M equal to IA. M is equal to IA. In such a case, your B becomes equals to mu naught M divided by 2 pi x cube. Mu naught M divided by 2 pi x cube. After this, what we do, we deliberately multiply numerator and denominator with 2 by 2. So it becomes mu naught 2m divided by 4 pi x cube. Okay, 4 pi x cube. Done with this much, children? We are done actually. Now we have some comparative statements which we will write. This part is also done. Now we come to some comparative statement. Now you write, compare with electric dipole. Number 5. Number 5, we say compare with electric dipole. So let's do our comparison with electric dipole. Then you write electric field on the axis of a dipole. This you have done. Electric field at a point on axis of a dipole. Do you remember the derivation? You had a dipole and then you found out the dipole was like this and on the axis an equatorial plane. So electric field on the axis of a dipole E is given as 1 by 4 pi epsilon naught 2p by x cube. What is x? X is the distance of the point from the center of the dipole. This is electric dipole. This is the value of E. E is equal to 1 by 4. So at this junction, just compare what did you find out for a magnetic field. Just see the magnetic field. The magnetic field came out B equal to mu naught by 4 pi 2m divided by x cube. This is what is going to give us the story. So we say form is same. Form is same for E and B for a electric and magnetic. Okay, rather than writing it like this, we'll say form is same. Okay, form is same except, sorry, same except this is electric field and this is magnetic field. Form is same except the electric dipole changes to magnetic dipole. In our case, electric field E changes to magnetic field B, and we have 1 by epsilon naught changes to mu naught. Now see the logic, children. This is the expression for electric field due to an electric dipole. Electric field at a point on the axis. Now this is the magnetic field at a point on the axis where you are getting the magnetic moment. And since the form of both the equations are same and is just accept these terms, therefore you say that therefore current carrying circular coil behaves, or circular loop, we'll go by our statement, circular loop is a magnetic dipole. Is a magnetic dipole. You can also see in summary, you can also see for equatorial. For equatorial. And in equatorial, the electric field is given by 1 by 4 pi epsilon naught P by x cube, whereas the magnetic field is given by mu naught by 4 pi m by x cube. This is in equatorial. So if you finally see as a summary, if you see as a summary, the axial field, the field at axial is always twice the field at equatorial. That's all. What did we do here? We actually tried to find out a relation to understand why a current carrying circular loop behaves like is a magnetic dipole. So our idea was that it behaves like a magnet when you view it from far away. How do you know something has a magnet? Something has a magnet when there is a magnetic dipole moment associated with it. So you first take what is the magnetic field due to a circular coil, and then you try to get rid of R1 by taking the point far away, so that your R square becomes negligible as X square, and the entire r square term can be replaced by a. So the idea was to bring a so that I and a can be taken as m, multiply both by 2 and 2 so that it gets the 4 pi. You have a 4 pi here also, you have a 4 pi in the electrical also. So you find that the electric field is given on the axis as 2p by x cube. Here you got 2m by x cube. Similarly on equatorial you will get p by x cube. Here you get m by x cube. So based on this analogy and these similarities, we say that the current carrying circular loop is a magnetic dipole. Clear? Our next one is to study one instrument which is a galvanometer, and that galvanometer is called a moving coil galvanometer. Sometimes you get some problems also, but they are very, very easy problems. Moving coil galvanometer. Now if you study electricity at higher classes, then there are two type of instruments, moving coil and moving iron. You know what is a meter? A device has got a pointer. So the pointer can be a part of the coil. There's a coil and the coil is pivoted so that it can actually move. When the coil moves, the instrument is called a moving coil instrument. And if the coil does not move, but if an iron moves, then it is called a moving iron. Moving iron we don't study in grade 12, we study a moving coil galvanometer. Okay, so a little bit drawing is there. So let's make our diagram first of the moving coil galvanometer. Quite easy, children. All you need to make is make some magnets. Okay, and similarly right. Right. Now this is a part of your magnet, and this is a part of your magnet. Let's say this is the north pole of the magnet, and this is the south pole of the magnet. Okay. On this, we will have what do you call coil. You're seeing it from a top. Okay, let me make it first, then I'll make you understand how to read this item. We'll do the labeling along with you so that you start understanding what Acha, one line that I wanted you all to, if you have done this, then just note down one line for the previous thing. Okay, for the previous, though I spoke about it, but just write it. That loop is an element, loop is an elementary unit for a magnetic dipole. Loop, you can't cut this loop, okay? The loop is an elementary unit for a magnetic dipole. Loop is a elementary unit for a magnetic dipole. Unlike the electric dipole where charges are elementary unit. Unlike the electric dipole where charges are the elementary unit. Children, let us understand this line once before we go ahead. Have you written? So just revise what you wrote. See, if you want a magnetic dipole, a loop is an elementary unit. You can't cut the loop. That is a mandatory unit. Elementary means it's the base unit. You can have many loops, that's a different. Now try to think about one loop. This is needed to create a magnetic dipole moment. And magnetic dipole moment means two poles will be there. Now go to grade 10. If this loop is carrying current, don't you see clockwise south and north on either side? Whereas the electric dipole moment, the elementary unit were two charges which were separate. Therefore, unipole, unicharge polarity concept is there in electricity, but not in magnetism. Magnetism dipole to exist, you need to have a loop. Whereas in electricity, you need the same dipole which is created by two charges. So the elementary are two charges. Here it is loop. Your cooking starts with two loops. Okay. So let's label this diagram. Okay. So these are our permanent magnets. These are our permanent magnets. And look at the shape of the permanent magnets. They are given circular so that you can create a radial magnetic field. We'll discuss about that. Radial. Every time the coil, this coil and the magnet should have a radial magnetic field, then only the angle will be 90 degree and sine 90 will be equal to 1. Okay, we'll see why we need that. Okay. Then all these red lines actually represent uniform radial magnetic field. This will be very important. We'll see that uniform radial magnetic field. And then the green one which I have twisted out here, this is basically the coil. The coil. Then I have a white circle, and the white circle is known as the soft iron core. Soft iron core. Right? And you would definitely also have a pivot out here. Means this can rotate. The coil can actually rotate. So it's pivot. Soft iron core. This is your pointer. The pointer is a part of the coil. This is your scale. This is your scale. Pointer, scale, permanent magnet. And then the yellow one, the yellow is a spring. We will see why we need the spring also. Spring. So you are studying moving coil galvanometer. Studying a moving coil galvanometer. Are we done? So write down what is the job of a galvanometer. So write galvanometer. Galvanometer has two jobs. One is detects a small current. You remember we had this in the meter bridge. Detects a small current in the circuit. And it can also be used as an emitter. If you can detect current, you should be able to measure current also. Used also as an emitter for measuring just one condition, measuring very small current. Means in milliamps, no? Very, very small current. You can't measure some 5 ampere, 2 amperes and all. Very, very small. So are you understanding, children? Look at the concept. I have got a magnetic field, external magnetic field, right? And I have got a soft iron core. The soft iron core is to concentrate the magnetic field. And I have got a coil. So whenever you want to measure the current, you will actually, this coil has two leads out here. And you actually introduce the coil into the circuit. So that a current, any current which you want to measure, the current will be flowing through the coil. And a current carrying coil placed in a magnetic field experiences a torque. Will experience a torque. Torque will cause it to twist. So if you are twisting on one direction, change the polarity of the current, the torque will be on the opposite direction. But look the idea of mechanics. Now you gave current to this coil, coil experienced a force, so it went and showed a mark, right? Don't you think if you take out the current from the circuit, it should come back? Why will it come back? No, I pushed you with a force out here. How do I expect you to come back? Think mechanics now. Ultimately you are experiencing a force. So I pulled you by your hand and I brought you here. Why will you go back to your place? Now think another thing. On your trouser hook, I have tied a rubber band and I brought you till here. That is the spring's job. The spring is called a restoring spring. So when it will rotate, it will twist the spring and go. So when you remove the current, the spring will be powerful and it will pull it back. Have you understood? So it's called a restoring spring. So shall we start? The principle. Now write down the principle, children. Principle. These things I'm not writing, you write down. A current carrying coil placed in a magnetic field experiences a torque. Current carrying coil. We initially had started our discussion with what? One loop in the previous class. IAB sine theta. Then when it is a coil, it is NIAB sine theta. NIAB. Do you remember? A current carrying coil placed in a magnetic field experiences a torque. And the torque will be causing the twisting effect, pointer will move. But there is one issue. There's one issue. You have to design this apparatus in such a way. Let's say this is small current, large current. If you increase the current, the torque should be proportional to the current. Are you getting it? The torque should be proportional to the current. Now, what is the value of that torque? That torque we had found as what came out as NIAB, NIAB sine theta. Now, if you don't have this as radial, suppose the magnetic field is not radial, you have made it radial, then you have different thetas at every orientation of the torque of the coil. Different thetas means different torque. So you will not have a proportional relationship between. See, what is the job of a measuring instrument? A measuring instrument finally say, let's see the fuel gauge of your car. As the fuel comes down, the gauge should also come down proportional. Otherwise, if this shows erratic, then it is not a proper measuring device. So in order for any measuring device to be working, we should always establish a linear relationship. Your body temperature goes up, the mercury goes up. You cool down, the mercury comes down. You can't have quadratic and all relationship. And another thing that we will want is good sensitivity. What is sensitivity? Small current also it should detect. We will see that in mathematical terms, right? For a small current, you should detect. That is one I want. Next, you should be linear. Now, to address the linear part, we make it radial. I'll make you write, but you first understand. Radial magnetic field ensures that the angle is always the theta, NIAB, NIAB, IAB, A and B. A is the area element, the current element of the coil. I is not a vector quantity. A is the vector quantity. A and B makes 90 degree always. Whichever orientation the coil is moving, the angle is always 90 degree. Have you understood? So have you written the principle? Now write the construction. So let's write the construction. The construction is, number one, you have a rectangular coil. Rectangular coil. The job of this rectangular coil is to carry current I, and another job is to freely move. Means basically this item is pivoted. This pivoted. Then the next one is soft iron core. Soft iron core. Its main job is make magnetic field stronger, make B stronger, and the next one we just discussed, make B radial. Make B radial. Then we have a spring. Spring has two jobs. One is supplies current to coil. So the spring is connected to the coil. Supplies I to coil. And number two, provides restoring torque. Restoring torque. That is tau R. Restoring torque. And then you have a pointer. You have a pointer, and the pointer shows deflection on scale. You know, in engineering, we have a chapter, we have a subject called measurement in 4th year. There, you actually you are not seeing things so seriously. See, this is called an elliptical gauge. You also get circular gauge. There are many meters which are circular, but if you see an old Fiat or a Maruti 800, then you will see the gauge is elliptical. A Honda City has a circular gauge. Circular torque measurement and sensitivity is different, elliptical is different. So many ways. Nowadays, everything is electronic because you are having a transducer and that maps it. But earlier days, we used to have it all mechanical. Okay? चलते हैं. So this part is done, construction and all about galvanometer. We are done. So I'm making it small. Right? Moving coil, galvanometer. Okay. Next point, write down, children. Why magnetic field is radial? Why magnetic field is radial? Why is B radial? So you know the answer. Now you can write. Without a radial field, the torque will be equal to NIAB sine theta. Sine theta. NIAB sine theta. Theta changes as theta changes, I changes. Okay. So current will not produce proportional deflection. Current will not produce proportional deflection. All right. If field is radial, then B is perpendicular to coil plane. or rather we cannot coil plane because it is coil's area vector, so it is perpendicular to plane. So B is perpendicular to plane, theta is equal to 90 degree and sine 90 is equal to 1. Your job is solved. So torque is equal to NIAB, means now you have a constant torque for a constant current. So the current is constant, but torque is also constant. Next topic is restoring torque. Restoring torque. Force is equal to Kx. In grade 10, 11 you must have written. For a spring, the restoring force is always Kx, where K is what, beta? K is the spring constant, X is the displacement. Restoring force. Now you are doing restoring torque. So restoring torque, tau R will always be equal to K into theta. Not theta, phi. Not theta, phi. Where K is spring constant. K is spring constant and phi is angular deflection. Did you understand what is the angular deflection? Means how much your pointer deflected. Phi. So at equilibrium, the turning torque, or whatever you say, the driving torque must be equal to restoring torque. Driving torque must be equal to restoring torque. So you can say tau D should be equal to tau R, which means niab should be equal to K phi. Niab should be equal to K phi. So the phi that you are going to obtain, how much your particular machine will rotate, is given by NIAB divided by K. NIAB divided by K. I'm writing it something like this: NAB by K, putting it in bracket, and I. So you got your right thing. The deflection, if you see this quantity, children, this whole quantity is basically constant. This is constant. So you're getting deflection is a constant scalar multiple of I. That means deflection is directly proportional to I. Your machine is doing its job. So from here you can say, we can say phi varies with I. Did you understand what finally we have done? The deflection of the coil is proportional to the current that you want to measure. And to do that, you just had two things: the soft iron core to ensure that the magnetic field is radial, theta is 90 degree, and the restoring torque will be given by the spring, which is K alpha, and K alpha is equal to NAB by NIAB. So K alpha, K phi. So phi comes as this. I'll change screen now. Our next job is to study something called sensitivity. Sensitivity of the galvanometer. What do you understand by sensitivity? Sensitivity is, main definition of sensitivity is deflection produced per unit current. Sensitivity means deflection produced per unit current. See children, when do I call a device very sensitive? If the device has the capacity to measure even a small current. So it is deflection produced per unit current. How much of deflection are you producing? if my deflection produced is very less, then I will say my sensitivity is less. Slight current, it should deflect. All right. So sensitivity can be defined as deflection, that is phi produced per unit current, phi by I. And phi's value, and phi, what did you find the value of phi as? NAB, there was an I out here, and you also had a K, and this I is here. So I and I cancel. So sensitivity is NAB by K, where K is the spring constant. I didn't get you, come again. Oh, it's just sensitivity. We don't say any denotation. NAB by I. Now, if you want to increase sensitivity, So if you want to increase sensitivity, what all you can do? Jack up the number of coils, jack up the area, jack up the magnetic field, or you reduce the spring constant. Look, if the spring constant means what? If the spring is very tight, just put a common sense. If the spring is tight, will the coil not find it difficult to move? Yeah, that's why you are trying to reduce it. Zyada tight spring lagayega to the coil will not move at all. And now the interesting part. Conversions. Conversion of a galvanometer to an ammeter. Conversion of a galvanometer, and this will use a typically grade 10 knowledge, nothing more than that. Right. So the first thing what you should do, connect the galvanometer in series, because ammeter is also connected in series. Let us say I have a circuit. Now I am bringing my galvanometer, and I will connect the galvanometer in series with that particular circuit. And there is some load out here. This is the load. So you're connecting the galvanometer. Now, what is the next thing that you used to know? An ammeter should have very low resistance. This is not an ammeter. You have brought somebody to work as an ammeter. So you now need to decrease its resistance. Right? So how do we decrease its resistance? There's a very nice thing. We will put another resistance in parallel with it. This is a low resistance. This is a low resistance, and this resistance is called a shunt resistance. You can write a shunt is a low resistance connected in parallel with a galvanometer when you want to convert it to an ammeter. When you want to convert it to an ammeter. Now listen. Here you have to understand two things and you have to write on your own. Now children, I have an ammeter. In my ammeter, I can measure any current. Do you agree? Because ammeter is supposed to measure current. Today I don't have an ammeter. And so I brought a galvanometer. But there is one problem with a galvanometer. A galvanometer can only measure small current. If you allow very high current to pass through the galvanometer, the coil will burn. So this you have to write. A high current will burn the galvanometer. Right? What is a galvanometer's job, beta? To measure small current. A high current will burn the coil of the galvanometer. But how are you sure that the circuit in which you fitted this galvanometer actually carries a current which is safe for the galvanometer? I don't know still. So what I did, I connected a low resistance in parallel. Now when the current flows till here, it's like water. It has two channels to go. Current always goes by the low resistance path. So majority current will pass through the shunt, thereby leaving very small current to pass through the galvanometer. And it will make my stopgap arrangement of using it as an ammeter. Understand once again, two things. Anyway, by connecting one resistance in parallel, the overall resistance is coming down. galvanometer itself also has a resistance. Every device has a resistance. With that resistance, this shunt is now becoming a parallel. But the shunt is not chosen to be high value. Shunt is chosen low value, so that whatever current is in this circuit, let all the current go through the shunt. The shunt is almost like a wire, and very less current will flow through the galvanometer, thereby keeping my galvanometer safe. Right? So first thing we say, we do not connect galvanometer to measure high current, because a high current will burn the coil. And second, we use a low resistance in parallel with a galvanometer, and the low resistance is called shunt. Locomotives in a railway yard which just move, they are called shunting engines. So the shunt will actually allow majority of the current to pass through. If you want, you can write down, current prefers always a low resistance path. So majority of the current will go through the shunt, and only safe current will flow through galvanometer, and the galvanometer is protected. This question is very common in 2 marks, 3 marks. Define a shunt and what is its use. A shunt is a low resistance connected in parallel with a galvanometer, and the use of it is to provide an alternate path for majority of the current to pass through when the galvanometer is connected in series, thereby ensuring that very small current passes through the galvanometer and the galvanometer remains protected. Have you understood? Very good. Okay. Now, my next job and the last topic is conversion of galvanometer to, I want to convert it into a voltmeter now. I want to convert it into a voltmeter. So what is the first job? Let's say this is my circuit and there is a load out here. This is my load, and I want to find out what is the PD across the load. So voltmeter is always connected in parallel. Do you agree or not? Voltmeter is always connected in parallel. So the first job I will say is that connect in parallel. And the next job says, look, no current should flow through the voltmeter. So what will I put here? I will put here a very high resistance in series, high R. And this resistance is called a multiplier resistance. Multiplier. You have put a barricade, and the barricade makes you understand that no current is flowing through the circuit. No current is flowing through the circuit. And you will put something which is known as a multiplier. Multiplier. And here you are putting a shunt. Shunt is in series, shunt is in parallel, multiplier is in series. Okay, bacha? So let's now calculate what should be the voltage sensitivity. Voltage sensitivity. What was current sensitivity? Deflection per unit current. So this will be deflection per unit voltage. Yes or no? What is deflection? Deflection was NAB. I was kept separate, and there was a K, and this V has come. Agreed or not? So if you see this, I can write it as NAB. What is I by V? The circuit overall resistance multiplied by K. I by V is 1 by R. And this R is the multiplier resistance. So if you want the sensitivity to go up, at that moment your resistance has to come down. Voltage sensitivity, so NAB by KR. And there is a small logic that we will also see here. Now see the logic. You know what is voltage sensitivity? You know what is this, okay? Now, suppose N is doubled. You double N is doubled. Number of coils is doubled. Let's see the current sensitivity. Current sensitivity. Don't you think the current sensitivity, if you double it, the current sensitivity gets doubled? it will also become 2 NAB by K. So if you double the number of turns, the current sensitivity is double, means your machine has become super sensitive now. Do you think it has also become super sensitive for voltage? That's the question. By changing N, you made it super sensitive for current. And look at for voltage, it is NAB by RK. Here also N has become double. No. In case of voltage sensitivity, this is very interesting. Voltage sensitivity, N has become 2N. Don't you think the length also has become twice the length? Yes. And resistance is proportional to length. So your resistance has also become 2R. R has become 2R. Therefore, here the voltage sensitivity has become 2NAB divided by 2RK. 2 and 2 cancelled. Yeah, no, it's not, while you are grammatically correct, but we should say an increase in the sensitivity of current need not mean an increase in the sensitivity of voltage. While you have increased the current sensitivity, it does not impact the voltage sensitivity. So galvanometer to be used as a voltmeter is not that a good choice. You can't play with the sensitivity. You have to play with some other thing, not with the turns. You can play with magnetic field, but just think, how can you play with the magnetic field? That is a permanent magnet. पूरा machine खोल के magnet थोड़ी change करोगे. You've understood this interesting part. If you increase N 2 times, the current sensitivity increases. But if you increase N, the length of the coil also increases, and resistance is directly proportional to length. So if your length becomes 2L, your R also becomes 2R. And that brings us to the conclusion of this particular chapter.